So we saw systems and how do we define systems and how are the properties of the systems defined. So in the previous lectures we saw about systems and what are the properties of the systems that are relevant to us and what are the properties of the resistors and inductors and capacitors of the system is what we saw. And then we said finally that linearity and the time invariance properties are very important properties that are satisfied by all three components, and hence we'll focus mostly on these two properties, and we'll call the systems that are satisfying these two properties as LTI systems, thus linear time invariant systems. These are systems which satisfy both linearity and time invariance property. Now we'll focus more on these systems and then study more properties of these systems and then analyze these systems more in detail, because of course we saw that the electric circuits and electronic circuits can be modeled as LTI systems because they satisfy these two properties, and hence these are more relevant to us. First we'll introduce a different kind of representation for continuous time signals, and this representation is going to be in terms of Dirac delta functions. So the Dirac delta signal is nothing but just a non-zero value at a particular instant and zero everywhere else, but with an area of 1. So this is what we defined as a Dirac delta function. Now what happens when you multiply this with some arbitrary function x of t? So the signal, when it is multiplied with the Dirac delta function, you basically get another Dirac delta function, but the area of this multiplied Dirac delta function is equal to the value of the signal at that particular point. In other words, x of t times delta of t is equal to x of 0 times delta. So the product here is basically another Dirac delta function, but it has its area scaled with the value of the signal at that particular point. Now what if we move this Dirac delta function to some other point? Let's say now we move this Dirac delta function to a different point and then multiply. So let's say this is t is equal to v. Now what will be the product? Now the product will be again a Dirac delta function, right? So whenever you multiply a Dirac delta function with another function, the product is going to be only a Dirac delta function. Only thing is that the area of this Dirac delta signal is going to be different. And what is that area? That area is equal to the value of your original signal at that particular time instant. What was the value of this signal at the time instant v? It is x of v. So now the area of the Dirac delta function gets scaled. So in other words, you can represent the instantaneous value of any signal analytically using Dirac delta functions. So if I have a signal x of t, then the instantaneous value at some time instant, let's say v seconds, x of v could be represented as x of v times delta of t minus v. Okay. So if I have a signal, let's say, which looks like this, a triangular function between 0 and 1. Okay. Now I can represent that pointwise at each time instant by a set of Dirac delta functions. Right? Something like this. So what have we done here? So we have taken this to be basically nothing but, let's say, some signal x of t, then we'll say x of 0 times delta of t, then x of 1 times or x of 0.1 times delta of t minus 0.1 and x of 0.2 times delta of t minus 0.2 and so on. Now can we get back this original x of t from all these instantaneous values? Of course, if you add them up, you have to get the original signal, right? Because these are all instantaneous values. So when you add them up, you have to get the original signal. So this is like slicing off a signal very finely. So you just take a bread piece and then slice off, you get individual slices, put together all the slices, you will get the original bread back, right? So that's exactly what we have here. So you take a signal, slice them individually very, very finely using the Dirac delta function. You get the individual signal its value at a given time instant. Now you put the values of the signal at each and every time instance and then add them up together, you get the original signal back. But then how can you add them up when the individual slices are infinitesimally small, meaning given a particular time instant B, what is the next time instant? It is arbitrarily close because this V can be 0.1 second or 0.001 second or 0.00001 second. It can be very, very small. So you cannot really add them up saying I'll add the first 1 second and so on. The only way to add them up is using the integration. So when you have multiple such signals together, you add them up and then you get the original signal back. And how are we representing that? We are going to represent that using this equation. Basically, we are decomposing a signal as a sum of scaled Dirac delta functions. Okay. Now, if we say that the system is linear, can it help in any way to simplify the representation of the system? Now if we say the system is linear, can it help in any way to understand the system more? Remember what we said is understanding of a system. If we can predict the output of a system for any possible input, then we claim that we have understood the system. So given a circuit, if you can compute the output of a circuit for any possible input, then you have completely understood the circuit, you have completely understood the system. Now how to completely understand the system? If the system is linear, can we somehow exploit this property to understand it easily? It so happens that we can. And how? Let's see that. Let us say that the output of the system for an input of this Dirac delta signal to be h of t. In other words, if I give the input to be simply del of t, the Dirac delta function, then the output is h0 of t. If I shift it by 1 second and give the input as a shifted Dirac delta function, then the corresponding output is h1 of t. If I shift it to the left, then my input would be delta of t plus 1, my corresponding output would be h minus 1 of t. So now I have a set of outputs for all possible shifted Dirac delta signals. Now given this set of outputs, can I tell what would be the output for any arbitrary input signal x of t? It so happens that it can be done if it is a linear system. Let's see how is that possible. First we will say that we are going to represent our signal x of t as the sum of scaled Dirac delta functions. So this is Dirac delta function at the time instant t scaled by this term. Okay. So this is the representation that we saw earlier. Okay. Now keep this in mind, tau here is the variable of integration. So you cannot use t here because t is present here after the integration. So the tau is the variable of integration. So once you integrate out, tau will disappear. So basically what we are doing here is we are defining delta in a temporary variable which is tau, okay, and we are defining x also in a temporary variable, multiplying them together, and the multiplied signal is what we are representing in t and then adding them together. Okay. So keep this in mind. So don't get confused with tau and t. Tau is just the variable of integration. It's a temporary variable. Alright, now that we have decomposed, we will use the properties of linearity. So what does linearity say here? The output of the signal, where the signal is a Dirac delta function shifted by tau seconds, is nothing but h tau of t. Now because it is linear, you can just multiply the input with some constant. The output should also get multiplied with that constant, right? That is the linearity property. That is exactly what we have used here. So this statement simply says that the input is scaled by a constant, then the output will also get scaled by a constant because the system is linear. Okay. Now what if I had two possible inputs? Now let us say the input tau1 produced an output h1 of t, and the input tau2 produced an output of h2 of t. Now what will be the output of the system for x of tau1 times this shifted Dirac delta plus x of tau2 times the shifted Dirac delta? Once again, we can use the linearity property, basically the superposition property, which says the outputs will not only get scaled, but the additive nature will remain as such. So this is when the input has two signals. The additive property comes as such. What if the input is a sum of infinitely many? So the summation here is basically an integration, and that summation still is retained because of the linearity property, and exactly that's what happens here. So you take the sum of multiple Dirac delta functions which are all shifted in time and scaled. So the output also gets scaled exactly by the same value and summed up. So what we have done here is now represent the output of a linear system in terms of the output of the same linear system for shifted impulses. That's all. So if you know the output of the linear system for shifted impulses, then you can find the output of the linear system for any input. How do we do that? Precisely using this relationship. Linearity helps us to do that. So now if you know the output of your circuits for shifted impulses, then you are done. You can find out what would be the output of the circuit for any possible input. But still, how many such shifted impulses exist? There are infinitely many shifted impulses, because you can have this value v to be anything. It can be from minus infinity to plus infinity, it can be anything. So there are infinitely many possible values that it can take. So even though we have reduced our complexity, we still have a lot of information to be known before we can completely understand this system. Can we reduce this? Can we simplify this even further? Yes, we can, because we have still not used the property of invariance. What if we use the property of time invariance? How does this get simplified even further? Okay, so the time invariance tells us that if the output of a system is h v of t for input delta of t minus v, then the shifted version of the input will also produce a shifted version of the output. In other words, if delta of t produces an output of h of t, then delta of t minus v would produce an output of h of t minus v. This is exactly the property of time invariance. So from this we can say that if the system is both linear and time invariant, then the output of the system for Dirac delta function del of t is all that we need to determine the output of the system for all shifted Dirac delta signals, right? So we have that h of t is in fact equal to the shifted version of h naught of t. That's exactly what we have here. So plugging that back to our equation of the output. So remember, this is what we got using the linearity property. Now we'll simplify that further with the time invariance property. Now we'll just replace this h tau of t with h naught of t. This is nothing but the output for the impulse which is shifted by tau seconds. Okay. So now this tells us we need to know the system's output for only one single signal, and that signal is the Dirac delta function. So if you feed in the Dirac delta signal, which is the impulse, and observe the output and let that be some h naught of t, you can use that to compute the output of this linear time invariant system for any arbitrary input signal. And how do you do that? It is precisely using this expression. All it tells you is that because I know what would be the output for a single impulse, I can represent any input signal as sum of shifted scaled impulses, and for each impulse I know what would be the output. So I'll keep shifting that impulse in time, scale it, and then add them together. That's exactly what we have here. So this is a very nice tool that we have learned, which says that if you want to completely understand an LTI system and LTI circuit, all you need to know is to know the output of the circuit for only one input. You just feed in this Dirac delta signal, your impulse, and see the response of the system to this impulse. And that is what we call as the impulse response of an LTI system. We'll denote that by h of t. So the impulse response is basically another signal. Okay, it is the output signal for the input being an impulse. If you know this response, which is basically the output of the LTI system for the input to be a Dirac delta signal, then you have completely understood the LTI system. How? Because to know any other output for any other input, all you have to do is just evaluate this integral h of t minus tau dt. That's it. So this is a very, very important property, and which we will use often in practice to understand what is the impulse response of the system, and from this impulse response we fully characterize the other properties of the system.